the basic idea was, you know, you have a timeline, you have multiple stimuli. What is the effect of this repeated stimulus on the perception of the next stimulus you hear? You can have different, in the time domain, you can have different kind of effects. So if you have a repeated stimulus and the last one is just a bit shorter, you actually perceive much more shorter. So there is a temporal distortion due to the period that is perceived. The discrimination of the rhythm increases, so you become better in discriminating rhythm or in discriminating temporal discrepancies, depending on how many stimuli you present. So if you have a very long, you know, a minute presentation of isochronous stimulus, always the same, and you present one stimulus which is just shifted a bit, it's going to be very obvious. But if you have only 3 stimuli, it's going to be hard to detect which one is just leading. This is also a very recent study that shows that, that what you perceive as a duration depends on what is the range of duration you experience over the course of the experiment. So somehow your time perception of one of those intervals depends on the whole distribution of time intervals you experience during the experiment. In the time domain, there is also this kind of interesting dualism. So what is a time point does not necessarily correspond to duration or to rhythm naturally. So you can have duration distortion, but they don't affect the perceived timing of the stimuli. And here instead I'm really interested in looking how this rhythmic presentation can distort when we perceive the stimulus. So we will try to have a rhythmic presentation to try to see how it influences timing of the, in this case, of the last event. What kind of distortion we can think of? Well, one of these distortions is that if you repeat stimuli, you might have a facilitation effect. So you have stimuli that are always in the same modality, they look the same, so at a certain point you present the n+1, well, you know what that stimulus should be. So your brain is already adapted, is already prepared to that, so it's faster to react. Okay? It's possible and being shown several times that can be called facilitation, priming, prior entry. There are several instances of this. The opposite is also true. So you might adapt to the stimulus, and then your perception can be delayed. So when you present a stimulus which is slightly different, then this strikes your attention and you react to it faster, so you perceive it earlier. Both these effects have been shown, but here what I'm really interested in is in this rhythmicity, right? You have a rhythmic isochronous rhythm, there's isochronous sequence, and I want to see whether we deviate a bit the presented timing of the last and what happened to the actual perceived timing of this last stimulus. So ideally, if you have an expectation, right, of when the next stimulus should appear, because the timing is always constant, when you deviate a bit, your brain should have this expectation, so should bring perceptually this stimulus towards the expected position, time position. So somehow, any deviation should be kind of reduced. I didn't say that, but it goes, of course, if you have any question or you have any comments, please by any means interrupt me, or if I don't explain something because I'm too excited, it's like, oh, look at that, tell me and I slow down. Is that enough embarrassing for the camera? Okay. So, first of all, we want to measure when you perceive deviation from isochrony, from this regular rhythm over time. So what we do is we shift the last stimulus in a sequence, we shift it a bit, and we ask the participant to tell whether this rhythm was regular or not. This is
you mean shift it temporally, right?
Temporally, yeah. So this is, let's see if it works. Sorry. Okay. Ooh, that's okay. I do it. I don't sing, but I do it with my hands. So. Okay. So that's an anticipated stimulus. The other is also possible. So we have. Okay. There was a long delay. So if a subject would have said that's an isochronous rhythm, now the rejected subject. Okay, so we have a range of asynchronies, and what we expect is participant to kind of say that the rhythm is isochronous at, in the middle of, so when the rhythm is actually isochronous, and as we deviate from this isochrony, we expect the responses to follow.
So why don't you have a 2AFC about the last one was sooner or later?
That will possibly.
Oh, okay.
Okay, and what we change is also the number of stimuli. So we have sequences of 3 or 4 or 5 or 6, and we ask, simply, is the sequence isochronous or not? And we perturb only the last one. Okay. So if we have 2 stimulus base and the third one is the one perturbed, okay, we have this sort of response distribution. So this is the asynchrony, this is the proportion of responses regular rhythm or isochronous rhythm. So it's, participants respond isochronous in a range of 50 milliseconds deviation, and then the response isochronous falls off. As we increase the number of stimuli that we present, you will see that this function becomes more and more steep. And in fact, the steepness is very much pronounced on the anticipated rhythm. So here, when the rhythm is, the last stimulus is presented a bit earlier, it makes a lot of difference how many stimuli you have presented.
Are these different subjects?
We have, this is, and well, it doesn't appear that there should be, so this is 12 subjects.
So I mean, it couldn't be that. I was just thinking, the one on the left, and then.
Oh no, this is within one participant, so it's all rowing. Because of this experiment, we don't ask to judge something at the end. We just ask them to judge the whole sequence. It's all interlinked.
But the fact that that's a steeper line there on that right-hand graph, that couldn't be just a practice effect, could it? Because
no, this is all
time.
So in one time you would have 3, and one time you would have 5. It doesn't. Okay. It doesn't matter. Okay. Yeah. So and every participant does all stimuli. So it's all completely interlinked.
So.
But the 700 milliseconds is always the same. So if
this one is.
Right, so if you have heard a 5, you know from the 3 already, you would get a crosstalk from that.
Yeah, why don't you get a practice effect then? Or do you get a practice effect?
Well, you judge. I mean, you do have practice effect, but still there is a difference. So this means that whatever process...
So what are those? Those 3 lines correspond to after 3, 4 and 5 or something? Okay.
Yeah, 3, 2,
okay.
3, so 3, 4, 5 and 6. Yes.
So even if you've been doing the task for like an hour, and it's always 700 milliseconds between them, then
you still have a change
that's
From 3 to 5.
for 3 to 5. No, it's not weird, because so if you have 3, no, I'm trying to explain it from a phenomenological point of view. So you have 3, you have beep, 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 right? And you have to say, is the deviation there, is there a deviation on the last one?
Yeah.
This is what you're asking, you're being asked. But then, when you have beep, 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 you are much prepared on what the timing is, and then you do the last one and you are doing the deviation. So you are very much prepared into this. And that's the puzzling thing at this point. And I'll show you more data that favors this hypothesis. So I'm going a bit ahead.
What's happening here in this task then is that as they're receiving each successive beat, and it turns out to be constant, each new one is constant, they know that the odds that the next one is not constant have increased, right? So what you're doing is you're almost improving the chances that the next one's going to be detectable as different, right?
Yeah, it's also so you can think about it in the detection point of view, but because we have different distribution.
Yes.
It's
Okay.
possible. How we read it in general, but I will show more data that favors this reading, is that you are building up an expectation on when the next stimulus should appear. So you know that is going to be the interval is going to be 700 milliseconds. But when the phase of this, you don't know. So if you have only two stimuli, it's two samples to reset your phase. You have third one, you set it a bit better. Fourth, fifth, fifth. Now the sixth one, it's.
So do you get a larger effect when the stimulus is more noisy, harder to locate temporally?
If it's visual, for example?
No, if it's audible.
Temporally.
Temporally.
Yeah. So
if you like just make it quieter, so it's just harder to locate, then you should get a bigger effect.
Well, you should definitely have the three flatter.
Right.
Yeah, but there should be a bigger difference between them. Shouldn't there as well? Yeah.
Possibly.
Yeah.
Possibly. Yeah.
Can I quantify that in terms, say, JND?
Yeah, so you can fit Gaussians on this, but the effect here. So if you compare point by point here, the effect seems to be especially at the front. So this is not really Gaussian, right? So it's the JND. You would have to fit two cumulative Gaussian. We were talking about this before, and look only at one side. So it's a bit trickier than just JND and PSS or point of subjective isochrony here, I would say. But yeah.
But that doesn't matter that you have two, because there could be an asymmetrical.
Yeah, but there is. It's just quite visual when you show the whole function. Okay. So overall, so here we show that there is a discrimination, that performance that increases with the number of stimuli, and this increases especially at the onset, so when the stimuli are presented earlier than the rhythm. So, but what we really want to see is how this rhythm changes perceived timing. So what we do is we do a TOJ task. We have a stimulus in one modality which is repeated, and then we have a comparison stimulus. So three repeated stimulus still with 700 millisecond interval. This repeated stimulus could either be audio or visual, and then the last stimulus in the sequence, it's out of sync, as in this case, but only of these 5 asynchronous. So what the task looks like, so this is the stimulus sequence for an audio repeated sequence. We have different comparison in different trials, so the comparison could be a flash that appears in any one of these points. And the task for the participant is just to judge at the 4th beat, they have to say whether they perceive first audio or visual. It didn't matter what was the sequence like. It could be a flash or a deep sequence. It didn't really matter. At the 4th stimulus, they had to do a temporal judgment. So we kind of balance attention, we have effects. So here what we expect, if we block this asynchrony, we have a proportion of responses. And this could be audio first for the participant point of view, or visual first. So here is, we recode this from audio first to final before comparison, so we can directly compare audio sequences to visual sequences. From this cumulative function, we have the center there, which is objective simultaneity, and we have a subjective simultaneity, which is the 50% point, so the asynchrony at which you have to present the light so that it's perceived to be synchronous with the subject. And we're going to look at this value in the next slide, because what we do is we present the last stimulus a bit too early or a bit too late. Okay? And we always compare it with the physical thing, which is always 0. Okay, let's look at prediction. So if this expectation that we have looked before is actually changing the perceived timing of stimuli, what we expect here is that if the stimulus is presented, the last stimulus is presented too late, this psychometric function should be shifted earlier, because the perceived stimulus is shifted earlier in time. So when you match it with the visual, the PSS should be more negative. If the stimulus is presented too early, then the shift should be positive. The interesting thing is, if we code standard comparison, then the same shift direction should happen if the light is presented too late or the light is presented too early. Okay? So let's look at the results of it. So this is the range of asynchrony we presented. Here is the proportion of standard before comparison. We have this psychometric function, we fit it, and we derive a point of subjective simultaneity that we can plot there. Okay? This is for this kind of stimulus which is anticipated, and we can do that for other stimuli, for physically synchronous last stimulus with the beat, or physically isochronous. And you can see that there is a change in the point of subjective simultaneity. And we can go forward. We don't have to worry about this. It's not a file.
No, I don't think so. Not in this building.
Okay. So we can do that for all 5 asynchronies. So in this, on this axis is the asynchrony of the last beat with respect to the isochronous rhythm. So here is too early, so we expect a delay. Here is too late, and so we expect an expectation.
Can I just make sure I get this? So
yeah.
If there was no effect of the preceding stimuli, that would be a straight line. Okay, thank you.
And if there was, if you just would go with the prior, with this expectation, you would not hear the last or not see the last stimulus. You would have this diagonal line. Okay. So you can see that 1, 2, and 3, they are sort of in the middle. The 4th one is actually goes with the physical stimulus, so you don't use the expectation, or even you go a bit above.
So this is a strange. Is this a strange pattern? I mean, it doesn't feel like it's going like that. It feels like it's going down and then down a bit further, then up. Right.
Yeah, it is a bit strange. So it's not linear in all respects.
Or even symmetrical, right?
That's not even symmetrical. In fact, the effect is stronger when the stimulus is anticipated. Like in the previous experiment, where we found an effect when the stimulus was presented too early. Here is the same thing. When the stimulus is presented too early, there is a much bigger effect and a bigger time window where this happened than in this case.
So at the end, the last point there, that's not significantly different from the baseline, right? And that's when the last one is presented later. So is it like it's outside of the window, which...
Exactly.
Okay.
So in fact, you can kind of do the percent effect. So if you take the difference between these 2 points for each of the participants and divide it by this amount here, you have a sort of weighting between the expectation and the actual last stimulus. And this is what it looks like. In fact, this is slightly even below the expected direction.
So you're saying that your estimation of when the last stimulus happens is somewhere between where it actually happens and where you expected it to happen. That's exactly what you're saying, right? Except for the final point.
Except for the final point.
Yeah.
And I would like to point out also the size of this effect, which is, in the time domain, this is a quite big of an effect. It's like 20 milliseconds in the time domain. You are delaying perceptually 20 milliseconds a stimulus. It's a huge effect. Yeah. In percentages, 40. In other experiments, we reach 60%. It's quite strong. the funny thing is, if you do it with visual, it's exactly the same function. Which is kind of, so this is a visual rhythm measured with the audio beat at the end. So they kind of look like
What
this.
is the different offset?
The difference offset is because this is due to the point of subjective simultaneity. We recode the data so that it's standard for comparison. So when you present the light and sound physically synchronous, you actually perceive the sound first.
Right.
And that's usually 30 milliseconds, so this should be double that. Should be 60, because you double it. Are we sure that we are sure, right?
Yeah.
I think if we can't see any big flames, then
Oh, it's in the physics building, and
then it's fine.
nice detail. It went off around noon as well, and
Yes.
everybody was standing outside, so they're on number 2 today. There will be some happy faces
Oh,
out there.
that's why they're bringing out the beers and stuff. Okay. So we also did a second experiment where we increased the asynchrony of or anisochrony of the last beat, and we found sort of a kind of a small effect there. This is for about 100 milliseconds and no effect for 200. Here the function actually went a little bit on the other side, and that's because of prior entry. Because when you present always the audio modality, you actually expect the last stimulus to be audio, because you know that right in the experiment. So that data point there is due to this anticipation of repeated stimuli. And this would be the pattern for the visual range, which is much the same, but it's not really significant for these 2 points. But this was with 9 participants. We are running more data on that. But the pattern overall looks quite interesting.
Sorry, I didn't get it. What is this now?
This is with visual seekers.
Okay.
So this data is the data I showed you before.
Yeah.
This data here is
Oh,
the
you
data
just
with the
changed the
second
range.
experiment with larger range. And the brighter line is the visual, which is noisier in general. The CMDs are a bit higher, so it's a bit trickier. Here I'm kind of reminding, but it was already mentioned that the effect is mostly on the stimuli that are anticipated. It falls off very quickly when the stimulus is done. So far, I showed you that regular rhythm affects the perceived timing of stimuli. Interestingly, this expectation works for within modality stimuli, because it doesn't. If this expectation would extend completely to all stimulus modality, we would have no effect. So if I expect, I have a rhythmicity, and this rhythmicity primes what should happen in any modality, then the effect would be the same on the audio and on the visual, so you would have no change in PSS. Instead, here we really show that the repeated auditory stimuli have an effect on the auditory stimuli, or mostly on the auditory stimuli, and that's why we find a change in perceived timing. The other result is that small deviation from isochrony are perceived to be diminished, so the perceived timing of stimuli is shifted towards the expected time. And we can call this like a temporal expectation of when stimulation appears. And there is more deviation with anticipated stimuli than with delayed stimuli.
So are you going to tell us why?
Yes.
Okay.
There is one problem, right? TOJ, they can be biased. So one thing we wanted to make sure is that we didn't have a bias result. So we asked a different kind of question to the participant. We rerun exactly the same experiment. And we asked participants to judge whether they perceive the stimuli to be simultaneous or not. It's trickier to fit, because that's, again, is not a real Gaussian, so you have function like this, with this root and finding the maximum always. But the results are very similar. And actually, if anything, they look a bit more slopier for the visual. So there is the same tendency. I wouldn't speculate too much on the actual shape of this because it's definitely noisier. But overall, it shows that there is the same effect. So the effect of stimulus repetition is also present with an unbiased task. So it's probably a real effect, this distortion of perceived timing into expectation. So how do we think about this? How do we explain it? And this was so a bit of thinking of how we can put this in Bayesian terms and how to explain this. We have two stimuli at a certain time. When you have two stimuli at a certain time, you actually, because the experiment is all about rhythmic stimuli, you actually expect the next stimuli to be at a certain time. When this stimulus actually appears at that time, you actually reinforce this expectation. So you have a steeper expectation for the next beat, okay, and so forth for the next beat. Okay. Now comes the time that the stimulus is actually not presented at the perfect time. It's a bit off. So what does your brain do? Well, it takes this new information, which we can call likelihood function, described there, and it mixes it or it integrates it with this prior expectation. So you have a posteriori estimate of the time of the last stimulus, which is a combined between the two. Okay. So does this?
How do you combine these two and get a number?
These two?
Yeah.
Well, you point. Let's say you point multiply every. If these two are Gaussians, right, and you point multiply every position underneath this, you have another Gaussian, which is just the weighted average of the two, and the weights. Where the location of this would be inversely proportional to the variance of the distribution, so the shape of this function. As a matter of fact, we show that the effect is not symmetrical, and so either one of the two is not Gaussian, or we have another factor.
So
Yeah.
did you actually mathematically derive that blue function?
No.
Or is
No,
it
no.
just speculative? Okay, sorry.
No,
I
no.
just thought.
Not yet. To do that, I mean, there are a couple of ways of doing that, but you need a lot. You
Yeah,
need
that's
very,
fine.
very
I just
precise.
thought you just derive that blue value. I just
No, in a sense, I mean, this is not from data. That blue line comes out. I mean, mathematically it would fit, but it's not based on the data. Yeah.
Whether the effects are shown in the first experiment, that basically you still find an effect where there's 3, 4, or 5 sequence, means that you're basically forgetting this prior from one whatever trial to the next.
Okay. I skip this and I show you the next experiment. Actually, let me skip one experiment and show you this. So here we look at the strength of the prior. We measure it in different blocks because we want to do this temporal order judgment, but we find out that if you do the temporal order judgment on the first stimulus and then the next stimulus is before, you have a big attention imbalance. So we do this blocked. And we have only two asynchrony of the last beat, so it could only be presented a bit earlier or a little bit later, never at point time.
Sorry, what did you say went wrong when it wasn't blocked?
So it's very hard. So when you have two stimuli and then the deviated stimuli that you have to do the temporal order judgment,
Right.
right? In one in one stimulus, and then in one trial. Then the next trial is the sixth. So you are constantly waiting for the next one, and you don't know which one is
You
going
never
to
know
be.
which one is the target. So that's
Exactly. So
makes it hard.
it's just from, yeah. So JMDs were changing a lot from the 3 stimuli to the 6 stimuli, but this was not the case when we blocked it. So we inferred that it was a problem of the experiment, of the trial by trial repetition. So if we look at the PSS here, what we find is the 2 PSS for anticipated and delayed stimuli, they kind of shift apart. So for 2 repeated stimuli, we have basically 2 and 3 repeated stimuli, we have basically no effect, or no significant effect. Here, the error bars are actually due to one very lenient participant, and the effect becomes bigger in size for longer sequences. Also,
So
we want to.
what you said,
Yep.
sorry, because if you back to that slide, so the standard error does not become smaller, because you said that because the anticipation, so the variance becomes smaller and smaller.
The standard error on the psychometric function.
No, I'm looking at here. I'm just thinking if I think your idea is when the beep first sounds, and so you have this anticipation, and your anticipation becomes more and more accurate. That's reflected in the distribution, which means the variance becomes smaller and smaller.
Yes.
So I just thought maybe that should be reflected in here.
No, because this is error bars
yeah, okay, I'm
across
sorry.
participants.
Yeah,
But
That's
so
possibly
to answer to that, there is a tendency. The effect is much stronger for when we do the intermediate. I don't show the data here, but there is an effect also when you do it blocked. Of course, when it was intermediate, it was like extreme. So the psychometric function really reflect the number of stimuli, but we thought that's why I don't show it, because it requires a bit of more understanding. But there is this effect, yes. We become better in temporal order judgment with longer sequences. But of course, your question was also, do you protract your prior from previous trials? And so to disrupt that, what we can do is we can have, within one session, have different durations. If your prior is based across trials, then you should have basically no effect. If your prior is at least in some part built within one sequence of 4 stimuli, you should have an effect. So here, the last stimulus is all, as before, only either 40 milliseconds earlier or 40 milliseconds later. Yes?
So if you've only got 3 different,
You could also
you
learn
can learn those
those
3
things.
different
That's
ones,
right.
or am I on a fast, medium, or a slow trial? You can
Yeah.
learn that.
You can learn that. Yeah, that's also possible. So you would suggest to run a randomized ISI
Yeah.
experiment. Yeah. You can.
Experiments.
But so again, so this is the difference in 80 milliseconds, and we have an effect. The effect reduces. So this is the percent effect, as I showed before. The effect reduces. 1 second is not statistically significant, but for the other 2 is still significantly. So there is still an effect of the prior, even when these trials are being interweaved.
So, but is it smaller?
It is smaller.
So it's partly within
Partly.
and partly across? Okay.
The experiment I skipped, and I would like to go back to. Sorry about those. Too much. Well, it's a nice animation. Sorry. Okay. Is it here? Yeah. So we have we have 2 different sequences. One where the sound was always the same pitch, and the other where the last stimulus had a different pitch. And what we also here there were the 40 milliseconds difference, and what we find is that the effect is significant only when the last stimulus has the same pitch, and instead there is a different pitch. We have no statistical significant effect. Okay, so I try to go back to where it was. Sorry about that. Okay, now we have, as we are saying, we have an experiment in which we know what the base duration is, or we know that there are 3 base durations, okay? And we want to play with this knowledge. So now we want to modulate your belief, or the participant belief, that the next trial is going to be isochronous. Okay? So what we do is we want to test whether the prior expectation depends on how many isochronous rhythms you have seen during the course of the experiment. So we divide participants in 2, and in one group we present 75 anisochronies that they cannot perceive. So they are very, very tiny anisochronies. We actually measured the J&B where they can perceive it to 75%. We present lower than that. And then we have another group where instead the anisochrony is really noticeable. Something like that. Okay? But in 25% of the stimuli, the stimulus is, the sequence is actually isochronous. And here they do, again, the same kind of task, but the last one is a bit off. So the critical test is to look at what happens with isochronous stimulus and see whether the expectation that you create from the other stimuli have an effect on this. So your belief that the next stimulus is going to be isochronous is modulating your time expectation for the next stimulus. So as I said, we measure, so this is the amount of perturbation we put to every single stimulus. We find the point where, here in this case, is 75% responses that the stimulus is anisochronous. And for one group, we present anisochronies which are the lot. So we have these 3 anisochrony that make up for 75% of the experiment. These stimuli here are actually isochrony, like all isochronies, and the last stimulus is perturbed, so we can measure the temporal mode adjustment as we did before. And we have a 30% effect here. So participants, when they see, a bit of perturbation and they are doing the task without perturbation, they still have this expectation, and this expectation change perceived time. Now, what happens when we perturb stimuli much more? So here we present these 3 anisochronies, which are much larger, especially in this case, we perturb 150 milliseconds, a base duration of 700, so it's definitely noticeable. And the critical test is this one, where we find virtually no effect. So here, even though we presented the isochronous sequence, and we do everything as before, but because in 3 out of 4 trials participants perceive an anisocronous sequence, then they don't apply this expectation because they still believe that this is not going to be isocronous. Of course, here we put a lot of noise, so you might question, well, this participants just doing crap or something, they don't pay any attention. So we can look quickly at the J&Ds, and they are plotted above if you can barely see them, and they are exactly the same. If anything, they do slightly better in the larger synchrony, large anisochrony group. But that's just variability across participants. Okay. Any questions? Basically, I would like to. Yeah.
Did you explain why it's lopsided then?
I didn't understand.
Why you have, you know, when you're showing your functions and the shifts were on one side of the function and not on the other, did you explain why that
Well,
was?
that is because there are two possibilities. The first, or even three. The first possibility is your expectation is not a Gaussian, so it's not symmetrical. Right? If you expect stimuli, for example, to be later than they should be, so you would have an effect that is stronger to pull back the stimuli in time.
Why would you have that then?
Why would you have that? That brings me to the second point, which could be a cost function. So your cost of being too early or perceiving things too early than they actually are might be higher than having it too late.
What?
But the third, but I'm gonna give you the third one. So the third one is much simpler. The third one is so you have a stimulus, right, which is presented earlier, and it's easy to wait a little bit and postpone perception for a bit. Okay. If the stimulus is presented too late, and you would want to anticipate it, right? So perceive it earlier, unless you do this post factum, so it has a post-diction kind of effect. But if it's online, and you have a stimulus which is not yet presented, and you want to perceive it now, because you are in between the prior, okay. How can we do that? So, this feels a bit weird. So this is the expectation at n, right? And you have the stimulus at n plus 1, which is presented here.
Yeah.
Okay? So here it's easier to shave a bit off and delay it. Here, if the stimulus is presented here and you are here and you want to anticipate this, it's trickier because the stimulus here has not been yet presented. So at time here, whatever time it is, and if the perception should be anticipated, you would anticipate the stimulus that is not yet there. So you can do that only when you are here and the stimulus is presented. So you can kind of increase this activation so that it's perceptible and anticipated. Does it make sense? No, you don't buy that.
I don't really understand it. It's not that I don't buy it, I don't really understand the explanation.
If you have a stimulus, in the sense that it's coming in, it's easy to delay it a bit. So
What do you mean by delay it?
delay it is you know, you put a higher detection threshold, higher criterion to perceive the stimulus. You turn down neural activation so that when you accumulate sensory information to perceive it, it's slightly delayed in time.
Yeah, I think that sounds reasonable. I mean, there's an accrual of information over time, right? And all you're doing is just almost turning the volume switch down on the accrual of information.
Exactly. But in this case here, if you want to anticipate the stimulus is trickier because the stimulus, you know, at a certain point, this is not yet there. So how can you anticipate the stimulus? So you can anticipate it slightly when you are in this area here.
So is that the same as saying that your noise, so that your likelihood is lopsided? Is it the same as saying that? You know that you can be wrong one way, but you're not likely to be wrong the other way. Is that the same as saying?
No.
Okay.
Wouldn't the simple, like a Weber function, basically explain that? Because the longer you wait, the more uncertain you get. So you can't be a Gaussian function that is on the line before.
For the likelihood or for the prior?
Well, you learn the prior from the likelihood, so in principle, well, I guess it would be for both. That occurs. So the longer that would predict if you now make an experiment with longer intervals than the 700 milliseconds, you should find less of that because the source is.
So you are saying the function here looks like
Yeah, it looks more like that.
and the prior also.
Right. Yeah.
So whatever prior you would have.
And I think that basically corresponds to less variance on that side where you have it, so more weight.
Yes. I agree. And so in this case though, so here you are assuming post-diction, right? So you are looking back at the time at the interval, so you know all the whole function.
Well,
Which I mean,
yeah,
it's an
but you
assumption.
also have to, if you model it prior, then you have to know the whole function, because you have to work with variables.
Exactly. Unless you have a more dynamic model like
No, if you use a different model, but in the Bayesian
In the
model,
Bayesian
so
model,
you
yeah.
need the distribution. How you get this?
Is it better?
No.
We buy that.
Yeah.
If you draw me a nice distribution now, that makes.
No, but so I think these are two kinds of explanations. One is, you know, if you look back at the old trial and you have the complete distribution, then yeah, sure, this could be an easy explanation. But if you are, you know, if the future is not written and you are at time here, right? You start a bit of likelihood. You have the expectation is right there, right? That's not the problem. You don't know the likelihood yet. Okay? So you have only this kind of signal. So this is easy to delay. You just turn the volume down so you have less activation. So when this increases here, you know, you go slower.
So could you test that kind of idea by changing the volume on the last stimulus?
Yep. We are doing that. It's tricky because, as I showed, if you change the frequency, the last stimulus is going to be perceived different from the rhythm, and this changes expectation. So what we are doing is it's actually things like AB, right? And the B. So this is strong, weak, for example.
Because you're saying that if you just change the volume, that means you throw away your prior.
Exactly. So if you do this, then the last one is still within the rhythm.
Right.
So you would have, you know, sort of, I don't know, this is the volume.
Yeah.
Right? So this is a weak last one. And of course, if you do this, right, this is a strong. But the expectation is exactly the same. Of course, you have to measure, you know, not only with strain, but with the, so we are running this. So I can't answer it.
Do you think you have a long-term sort of expectation of how likely something like this to happen, given that something has just happened then? Or does the prior only become into existence after two examples? Or sort of how?
Is that the same as saying you build it up within the trial or over all the trials, or not?
Kind of, yeah, because it's within the trial you're building this prior and then you're going back to the sort of beginning again of the beginning of the next one. It seems like from what you're saying that they were getting better and better even if you use the same timing across all of them. But yeah, is it just created kind of then and there?
So
some kind of long term.
So there might be some long term expectation of what rhythmicity is. In fact, other people have hypothesized that there are kind of functions that are called limiting cycle functions, which are oscillators, basically. And the rhythm, so the radius of this oscillator, you have several of them. So the radius is the base rhythm that this oscillator responds to. You have an attentional energy. So these are attentional models. I'm just linking to them because they have kind of the same fundamental structure. So you have an expectation for a certain time, and then this expectation, which is this function here increases over time. You see a lot of similarities, even though here, this is all parameterized in a different way, so it's not a Bayesian kind of model, but these are similar. So every time you've been presented with a new pick, a new beat, the phase gets shifted a bit in a certain proportion, depending, this proportion is depending on the variance of this function. It's interesting because these kind of models, they link also to music. And so you have weak beats and strong beats, which is the composition of Gaussians. So you have these three cusp models of what the prior should look like. So this basically would fit here and would go on this circle. So it's kind of nice music, attention, vision kind of connection. So this is there even before you start the experiment. What you do is you limit more the cycle depending on how much exposure to one rhythm you have. And then you squeeze this one depending on how many stimuli in the trial you see. I mean, I'm jumping back and forth, but another connection I would like to make is about neurons, because so far it's been kind of theoretical. So this oscillator, this leading cycle oscillator, is actually two neurons. Has been shown also by this guy here. So it's a very simple model, and by modulating these connections, you can change the limiting cycle. And in fact, this has been shown to have very nice predictions with rhythm made of light and sound, like this. And monkeys here were asked to pay attention to deviant vision or deviant auditory stimuli. They recorded on the cortex, and they have these rhythmic activations. I mean, I'm not an expert on this, I'm just showing this because of the colors. The point of this is, has the rhythm, this deviant stimulus was presented out of phase with respect to the rhythm, there was an increase in reaction time. So the attention allocation that was performed by these these blobs here made the detection of these deviant stimuli faster and more precise. So it's a long shot connection, I agree, but there is some commonality between the attentional literature, the music literature, and this neural literature, which perhaps can be better linked with the vision perspective. And just to conclude, I mean, my time is basically over. So isochronous stimuli create an expectation for similar stimuli. If you change the stimuli, this expectation doesn't really work anymore. The expectation is combined with sensory information to generate a perceptual estimate. The a priori expectation is acquired within a trial, but is enabled by the belief that the sequence is isochronous. And I would like to thank Darren for running most of the experiments, Stephanie, which she's a very good first-year student, undergraduate first-year student. She's very keen in running experiments. The Marie Curie, which gave me some funding this summer. Thank you very much. I don't know more. Yeah.
So, what is it? So you seem to be saying that it's kind of built in that you're sensitive to these regular rhythms. Is that fair?
Yeah.
So why is it?
I'm not the only one saying. I mean, there are people that say that your brain resonates as a whole to the stimulus. So you can record basically 1.5 hertz on the whole brain when you are presented with stimuli like this.
So, that's a crazy question, but within vision, I can understand why it's useful to be sensitive to things that are like equally spaced for making, like for understanding texture gradients and that. Why is it useful?
In audio?
Yeah, to be sensitive to this regular rhythm like that.
I don't know,
You
like
know,
this.
if you're about to have a heart attack or something?
You have a person approaching and you want to understand whether he's speeding up to attack you. I don't know, I'm just making this up. You want to understand. Yeah, you want.
Okay, that's quite good.
I mean, regular rhythms, right, as, in audio are actually more present than in visual modality. So, clocks, father clocks, no, they're called grandfather clocks, right?
Yeah, but that's all very recent.
I think music is quite tied to early communication.
That's kind of what I was wondering.
The answer. Okay, you pass.
I mean, also speech. I mean, the speech is also rhythmic. It has a very complex rhythm, but it is rhythmic.
So does that maybe help you to identify different speakers or something?
Well,
Is that possible?
also to give more meaning. I mean, music, for example, if you have strong beats and weak beats, it's just a small anticipation of it. You don't have to increase the volume or anything. It's just a small anticipation of one of the beats.
To be able to analyse anything from speech linguistically as a child where you've no formal instruction, you've got to be able to discern patterns amongst the speech signal across speakers, right? And I can't see how that wouldn't require, I'm not saying maps perfectly at all, but I can't see how you could do any form of speech recognition, and that's pretty old. I mean, I'm not saying it's as old as mankind, but it's been around for quite some time. But I think you would have to have, much more complicated systems, but this might be, maybe it's tapping into something like that.
Because then you have a sense of rhythm that you can scale up or scale down.
Exactly,
to
it's
different
mapping
speakers.
stuff on it, right? I mean, people can extract complex grammars from random sequences apparent, they'll look random sequences of letters or sounds. People can extract grammars, abstract grammars from them. Perfectly
Wouldn't that predict if animals that doesn't speak wouldn't be able to do the talk or not?
Well, I'm not necessarily.
No, monkeys can. But I mean, do they speak?
You're asking for an example of why.
Yeah, no,
sure.
I didn't want to help.
I guess speak it out.
Can you ask a question to someone else?
But also, if you even go into anticipation, you're constantly anticipating a certain timbre in the voice. A lot of humor is based on deviating from that, where all of a sudden the comedian does something slightly different with his voice to put emphasis or take it away, and then all of a sudden you realize that you had an anticipation there.
I mean, there are lots of naturally occurring, temporally periodic things, right? I mean, I'm thinking of waves on a shore and such like
walking.
that.
I mean, very
there's a
common
lot of it about
walking.
when you think about it more
Water
generally.
dropping,
Yeah.
water dripping.
It was a gift of a question, Okay, so, sorry, do you have a question?
Sure.
Go on, go for it.
Couple. No, because you went into music or speech, the rhythms you take are really, really very simple. Everything is the same. So if you take a little bit more complicated rhythm, just like, do you learn two priors in that case, or do you learn?
Well,
what do you learn?
I don't know exactly. If you would talk to larger, then you would put on this envelope here, this here you would put a double. You would put that. So in your case, the one you have done. So you would have this, and then two that are more closely, you would wrap it around there. If you think more about oscillators like these ones, then you know you can think you have a family of, I'm speculating,
Yeah.
a family of oscillators, each one with their own rhythm, and some of them tune to one of the frequencies, some other to the other frequency, and overall the balance of the two creates the overall prior expectation. So I don't have a definitive answer. There are several possibilities. At the moment, all of them are equally likely.
And probably just I don't know what to say about it, but there's a huge literature on the other side of producing rhythms like tapping or so.
Yeah.
Your colleague has worked a lot on that. So how does that connect to this
So the expectation
part?
is exactly the same. So we are also doing that actively. So you have an expectation, and you are producing your sensory feedback so that it matches your expectation.
Yeah. Do these models that they develop there, I don't know all of them.
Yeah, the only trick is that you can have the sensory signal and the prior, and you can look at the difference between the two. So you have your prior is now the oscillator that will drive your next output. When you actually produce the output, you have noise, motor noise, so you can look at the difference between your output and the prior and correct for that. And that works. It's the same formulas that Alan applied for his famous 98 people. So it's n-1 or t-1 correction. It's the same, exactly the same.